So as you remember, magnetic strength of a solenoid depends on what? It depends on the permeability of the object, the permeability of free space, the number of the turn per length of the solenoid, and the current carrying through the wire. Okay, the current carrying through the wire. So this is the formula that you are going to need to use it. Okay, the formula B equal is free space permeability times number of turns times the current of the wire. Okay, so let me just make sure. So then let's continue. Let's continue to magnetic force part. So what does magnetic force mean? First of all, magnetic force is the force that causes the object to causes the charge or object to like have a speed. Okay, so magnetic force depends on three. Magnetic force for a charge depends on the magnitude of the charge, the magnitude of the velocity, and the strength of the external magnetic field. Okay, in order to find the magnetic force for a charge, okay, this is for a charge, don't forget it, okay, don't confuse it. For a charge, you are going to use this formula: the magnitude of charge times velocity of the charge times magnetic field charge times, if there is a angle between like velocity and the magnetic field, we are going to put that over there as sine theta. Okay, you are going to use this formula to find the magnetic force for a charge. Next, we have factors determining the force on a current carrying conductor. This could be a wire. Okay, so there are factors which are affecting the force here. The first one is the current, the second one is the length of the wire, and the third one is the strength of the magnet. Okay, these three things affecting the force on a current carrying conductor. So here we have another formula. Okay, we are gonna have this formula: F equal magnetic force times current times length of the conductor times sine theta. Okay, this is other formula that we are going to use to find magnetic force. Again, this magnetic force for current carrying conductor, it could be a wire. Okay, the first one was about charge. Okay, if you are finding the force for a charge, you are going to use the first formula. If you find magnetic force for a current carrying conductor, you are going to use this formula to find the magnetic force. Yes, Adia.
Wasn't the
All right, let's continue. So, electromagnetic induction, the third part, electromagnetic induction. Remember, electromagnetic induction is the process that's creating current by using a magnetic field. Okay, we use magnetic field, we create current. This phenomena called electromagnetic induction. So there is magnetic flux and field strength over here. So in order to find the magnetic flux, we are going to use the formula magnetic field times area. Okay, magnetic flux depends on the magnetic field and the area. When we multiply these two, we are going to find the magnetic flux of a conductor. So the SI unit of magnetic flux here, remember the SI unit of magnetic field is Tesla, and the SI unit of area is meter square. So when you find the SI unit of magnetic flux, we are going to find it as Tesla meter square. Okay, this is going to be SI unit of magnetic flux. So there are two laws here that we need to know for the electromagnetic induction. The first law is the Faraday's law. Remember, the Faraday's law states that the size of the electromotive force involved is proportional to rate at which the conductor is cutting through the flux lines. Okay, to find the EMF here, this is EMF, this stands for EMF. To find the EMF induced current or induced voltage here, we are going to use the formula magnetic flux over time. And if you don't know magnetic flux, what are you going to do? You have to write magnetic field times area. So the formula will turn into magnetic force times area over change in time. This is going to give us electromotive force or EMF. It's going to give us induced voltage. Okay. On the other hand, there is Lenz's law, the second law of the electromagnetic induction, the application of the electromagnetic induction. This law states that the direction of the induced current is going to be oppose the change that is causing it. Okay, it opposes the change. It opposes the change. This is known as Lenz's law. Okay, Faraday's law and Lenz's law. These are the two laws that we need to know for electromagnetic induction. So let me just do something. So then we have inductors. Inductors, remember, these are the device which has two terminal electric component which store electrical energy. Okay, they store the energy, and this energy it's formed like it's stored as form of the magnetic field. It is a coil with several loops. So on the other hand, we have inductance. What does inductance means? Inductance, the property in electrical circuit where a change in the electric current through that circuit induces an EMF that opposes the change in current. Basically, this uses Lenz's law. Okay, inductance uses the Lenz's law for the for this phenomena. Okay, so there are two types of inductance. The first one is the self-inductance. Remember, self-inductance happens only in one circuit. So to find the induced current, induced EMF over here, we are going to use self-inductance times changing current over changing time. Okay. The second inductance, we have mutual inductance. For mutual inductance, there should be two circuits. And to find the mutual inductance, we are going to use a formula. Mutual inductance times changing current in the second circuit. Okay. The change must be in the second circuit. The change in current must be in second circuit over time. So this is going to give us EMF in mutual inductance. Okay. So then we have transformer, the last part of the unit 4, transformers. Remember, transformers used to arrange the voltage. Okay, they used to arrange the voltage. So there are step up and step down transformer. Step down transformer, they are their number of turns in primary coil less than the number of turns in secondary coil. On the other hand, step up transformer, number of turns in secondary coil is less than number of turns in primary coil. Okay. We have a transformer equation. The equation tells us like the output voltage over input voltage is going to be equal to number of secondary number of coils in the secondary number of turns in secondary coil to number of turns in the primary coil. Okay, this formula is important. You should remember this. You're gonna use it in the exam. Okay, this formula is important. Just use it. You will use it. You will need it. All right. Let's continue. Let's start unit 5. I'm not gonna solve any questions like if they are not necessary. Just I'm gonna tell you what you guys have to do. Okay. So let's just some parts I am going to solve the questions. So those parts, the questions are important because you know the questions. So unit 5, electronics. So first of all, thermionic emission. What does thermionic emission mean? Remember, thermionic emission was when you heat up a conductor, the electrons at the surface of the metal, they're going to escape from the metal. So this phenomenon known as thermionic emissions. So there are vacuum tubes. We learn about it. So vacuum tubes, let me tell you just a few examples of the vacuum tubes. So the first one was a thermionic diode. We learn about cathode rays, X-ray tube, we learn about it, and we learn about cathode ray oscilloscope. Okay, cathode ray oscilloscope. So there are some uses of cathode ray oscilloscope that you need to know. The first one, it works for the direct current. Okay. The second one, it works for sensitivity. So in order to understand the sensitivity, I just wrote a question over here. Let me just explain this question. What does this question mean? Okay. So for example, if the sensitivity is set to like 3 volts per centimeter and the spot is deflected by 2 centimeter by an unknown potential difference, the value of the PD must be 6 volt. How are you going to read this? Here, for example, you see you're going to check the axis. Okay, here there is displacement is 1. That's why it is 3 volt. Okay, for each square the displacement will be 3 volt. Okay, as you see over here in the second part, it deflected by 2 squares. When it deflected by 2 square, remember each square represents 3 volt. So the peak voltage here is going to be 6 volt. Okay, this is called sensitivity of the device. Let's continue. So finding the period and frequency of the alternating current or voltage using the cathode ray oscilloscope. This part is important. Remember the period. To find the period, we are going to use the formula 1 over frequency, and the SI unit of period is second, and SI unit of frequency 1 over seconds or hertz. There is a question. I just wrote a question for you guys to explain it better. Okay. So let's say the sensitivity of a cathode ray oscilloscope is set to 7 centimeter per second, 7 volt per centimeter. So the time base setting 1 millisecond per centimeter. So let's find the peak voltage and frequency of the AC signal over here. So there is a let me give you the figure over here. How are you gonna find it? First, let's talk about the peak voltage. To find the peak voltage, you have to count it from the origin, like this is our origin, from origin to top number of the squares. Okay. So how many squares we have here to the top? 1, 2, and 3. Okay. So that means to find a voltage, we are going to use 7 times 3, 7 volt per centimeter times 3 centimeter over here. Okay, each square represents 1 centimeter, so you are going to count from down to top. So the peak voltage will be 21 volt. Okay, second of all, we have to find the period in order to find the frequency. So to find the period is easy, because 1 millisecond per centimeter means for each part it is going to displace by 1 millisecond per centimeter. So for this part, you have to count between two peaks. Okay, number of the squares between two peaks. So look at here: 1, 2, 3, 4, and 5. There is 5 square over here. That means our period will be 1 millisecond per centimeter times 5 centimeter. Okay, when you multiply it, you are gonna find the period 5 milliseconds, and 5 milliseconds means 5 times 10 power negative 3 seconds. So in order to find the frequency, remember frequency means like when you crisscross it, frequency will be 1 over period. So when you do that, you're gonna find the frequency as 200 hertz. Okay, 1 over 5 times 10 power negative 3. When you divide it, you're gonna find the frequency of this cut ray as 200 hertz. Okay, this is going to be the frequency of the object. Let's continue. The fourth part, we learn about conductors, semiconductors, and insulators. So what does conductors mean? Remember, conductors are the material. Sorry guys, I lost the connection. I just got it back. Okay, the connection was weak. So let's continue. Let's continue where we left off. Okay. So conductors, semiconductors, and insulators. So conductors means material which allow the electricity pass through them. Remember, in their conduction band there are many free electrons. That's why they are conductors. For semiconductors, they have a few electrons in their conduction band. That's why they are not good. They are not like as good conductor as conductors. You can compare them. And insulators, on the other hand, they are the materials which do not allow any electricity or heat pass through them. Okay, insulated. They insulate everything, like glass, you can say, like wood, you can say. For semiconductors, you can say germanium, silicon. For conductors, we can say metals. Most of metals, they are conductors. Okay. We are gonna classify semiconductors into two parts. The first part are intrinsic semiconductors. So intrinsic semiconductors, they are pure semiconductors. They do not contain any dopant or semiconductor materials. Okay, they have 4 valence electrons. They are, for example, pure silicon is an intrinsic semiconductor. Okay, they do not have any dopant or anything else. They are pure. That's why they are intrinsic semiconductors. So the second type of semiconductors are extrinsic semiconductors. These semiconductors, we get them by doping. Okay, we get them by doping, like by giving them electrons or taking away electrons from them. This semiconductor is known as extrinsic semiconductors. Okay. So there are two types of extrinsic semiconductors, N-type and P-type. So N-type means like these semiconductors, their majority charge carriers are electrons. For P-types, their majority charge carriers are holes. Okay. Remember, semiconductors have both positive and negative conductors. Okay, they have both positive and negative carriers. We call the negative carriers electron and positive carriers holes. Okay, don't forget that. Next, we have forward bias and reverse bias. Forward bias means like when you connect a positive terminal of a cell to the N region of the diode. Okay, when you do that, and the negative terminal will be in the P region. So this is going to cause prevention of conduction. Okay, the conduction will not happen there. For the forward bias, on the other hand, when we connect a N-type, like P-type, P region to positive part, and N region to negative terminal. This is going to allow the conduction. So we call this forward bias. In the forward bias, there is conduction, but in the reverse bias, there is no conduction. Okay. So there are semiconductor devices. For example, diode, LDR, LED, transistor, and transistor. These are the some type of the semiconductor devices. Next, we have rectification. What does rectification mean? When we use the PN junction in a diode, this is going to allow the current flow one way. Okay,